Okay, so we're ready now to look at implementing the limit comparison test. And so here we consider this rational function here, 2k squared plus 3k minus 2 over 3k to the fourth plus 5k squared minus 9 as k goes from 1 to infinity. Now, if you were to look at this thing here, the numerator as k goes from 1 to infinity is always positive. The denominator actually, when k equals 1, is actually negative. But after that, this denominator is always going to be positive. So this thing is always positive terms. That's the first kind of requirement, right? Okay. Again, when I say the series we compare it to have positive terms, again, we mean after a certain point at least. So the fact that my first term there is negative, that's not going to contribute anything to convergence. After that, they're all positive. So as long as beyond a certain point everything's positive, that's all that matters. So we'd like to see whether this thing converges or not. Boy, would this be a pain in the butt to do with our integral test. Right? Wow, would this be not fun to do with our integral test. Think about the integral of this thing. Right? If I just did integral, forget changing it to x, of that. Wow. Wow, wow. Having nightmares yet? We would have to see, can we factor that denominator? Yeah, how does it factor? What kind of partial fraction thing can we use to break that up? How can we integrate the different pieces? Anybody excited yet? This would not be a fun integral to do. This would not be a fun integral to do. Not at all. But with our limit comparison test, we can compare it to another series that we know either converges or diverges. And from that, we can kind of make our judgment there. So the question is, well, what series am I going to compare it to? So what series am I going to compare it to? So what we do is we look at our series here, our expression. We kind of say, as it gets really big, what's it going to be roughly approximated by? And what's it going to be roughly approximated by? So as it gets really, really big, the only thing that's going to matter are the leading terms, 2k squared and 3k to the fourth. Right? That's all that's going to matter, right, as it gets really, really big. And that will just simplify to 2 over 3 times 1 over k squared. Okay? And we know something. 1 over k squared, right, it's 1 over k to the p, is a p series. 1 over k squared is a p series. And p is greater than 1. So we know that thing converges. So we're actually going to use the 1 over k squared, 1 over k squared function as our thing that we're going to compare it to. Okay? That's what we're actually going to compare our thing to, is the 1 over k squared function. Okay, so that's what we look for. So we kind of look to simplify this and see roughly what is that approximately. And so that's how we get our comparison guy right there. Okay, and so now that we decide we're going to compare it to the 1 over k squared thing, we do the limit of the one sequence divided by the other one. So limit as k goes to infinity of the one sequence, 2k squared, plus 3k minus 2 over 3k to the fourth, plus 5k squared, minus 9, all of that divided by our bk sequence, which is 1 over k squared. Basically what we're looking for then is one of two things to happen. 1 over k squared. We're either looking for it to approach a number. Since 1 over k squared converges, then our sequence would converge. Or we're looking for it to go to 0, in which case, since 1 over k squared converges, our sequence will converge. If we do this and the limit becomes infinity, then that means 1 over k squared actually wasn't a good choice, and we should maybe try something else. So here we go. So all this stuff being divided by k squared would be the same as multiplying by the reciprocal of 1 over k squared, which would be k squared. That would give me a limit as k goes to infinity of 2k to the 4th plus 3k cubed minus 2k squared all over 3k to the 4th plus 5k squared minus 9. And we say, hey, all that's going to matter are the leading terms when we do this limit. 2k to the 4th over 3k to the 4th. And so this limit becomes 2/3. And since the limit's a constant, they either both converge or they both diverge. Since 1 over k squared, the B sequence does converge, we know that our series converges as well. Okay, and that's really the power here of the limit comparison test. That's really the power of the limit comparison test. We can look at it and see roughly what are we. Well, it looks like we're roughly a k squared, 1 over k squared series. Okay, we're roughly a 1 over k squared series. Since that one converges, we check and see what happens to see what our series, whether it converges or diverges.